All right. Hello, I'm Tyler Linderoth. Nice to meet you all. I am a research specialist at Kellogg Biological Station and bioinformatics and statistical consultant for MSU more broadly. And I work with Sarah Fitzpatrick. And this project, I've gotten to work with all these other great folks. Looking at investigating how to use translocations as effective conservation tools. And so to get in the headspace, as habitats become fragmented, populations tend to decrease in size and become isolated from one another. And along with that, the populations tend to incur higher inbreeding, which increases chances for inbreeding depression. Effective population sizes become smaller, leading to more rapid decay of genetic diversity and reduced adaptive potential. And then there's also the demographic aspect where they have less of a demographic buffer to kind of environmental and demographic stochasticity. And of course, this is exactly the situation faced by Florida scrub jays, as much of their habitat has been wiped out. And I guess I don't need to introduce the M4 very much. That's the meta population that I'll be talking about, roughly in this western coast of Florida, which, as you know, it overlaps with land that's owned and operated by Mosaic. And just to recap, as part of the habitat management plan, it was determined that multiple subpopulations were inhabiting areas that had been degraded by agriculture and inadequate fire, and were actually operating as demographic sinks to this metapopulation, and they were inhabiting areas to be mined. So in order to mitigate for the mining, the strategy was to translocate all the scrub jays from these at-risk populations into a centralized area in the metapopulation where habitat had been restored. And in the course of doing so, alter the metapopulation structure to more of a mainland island model, which was, as Raul showed, supposed to increase the viability of the overall metapopulation. And so translocations were conducted every year between 2003 and 2006, and then 2007 to 2010. In total, 51 birds were translocated from these 5 sites into the Mosaic well field. And when I talk about the Mosaic well field, I'm going to consider the adjacent properties, the Duet Preserve and the Coker Tract, that are adjacent to the Mosaic as this core region. So I'll refer to this core region population. And actually, right before translocations were conducted, there was some small, what we call residents in the core region. So there's 13 individuals spread across 4 family groups that is what I call the residents. They were there just prior to the translocations. And so again, kind of the goals were, to preserve these lineages in these areas targeted by mining that were likely to go extinct as a consequence, and establish this healthy mainland population, which would help promote the viability of the M4. So what happened? Not much of a surprise now. As you can see, I think one of the great things about this translocation story is it really emphasizes the critical role of habitat management and just habitat in general, because it's pretty obvious. You can see how over time, new family groups established de novo territories throughout this available habitat, which supported this population growth. So you can here in the vertical line see the number of birds that were introduced or translocated, and which resulted in this 10-fold increase in the population size. But as Raul says, there was quite extensive monitoring. And what that revealed is that of the 74 contemporary population, when I say contemporary population, I mean the population kind of in 2022, right now, 2021, 2022, that, and when I say ancestors or founders, I'm referring to the residents or the translocated birds, the jays that were in this area that could have founded this new population. Of those 74, actually only 16 individuals or lineages have really contributed or have disproportionately, I should say, contributed to this population, such that, you know, starting from 2015 on, these individuals, their lineages that are colored in these lines, they've accounted for over 75% of this population's ancestry. And you can see there is a pair amongst these 16, there is a pair of, or two birds that were actually a breeding pair that stand out even amongst these 16. One was RLSK that was translocated early on from site 13. And you can see his breeding history there. He tried to breed with, I think this was another translocated bird, and they did fledge for offspring then, but then he didn't have very good fledging success, both with that bird and then a resident that he tried to pair with, or that he paired with. And then when WSAK was introduced in 2008, they paired up, and it was just kind of magic, I guess, where they consistently fledged. They just had, very consistent fledging success until basically neither of them were seen again. So presumably died. And so from 2008 on, after they formed a pair, that single breeding pair cumulatively has contributed or accounts for about 25% of this population's ancestry. And so kind of seeing that this whole process in a bit of a different, maybe very confusing way, each one of these rectangles is an individual that, and their height represents the proportion of the population's ancestry that they represent. So I'm just showing resident individuals. And so important to say is that there are three residents, these three different colors here, that are among those 16 highly successful contributors. So there is still resident ancestry in the population, but you can see that most of the resident individuals, they quickly start to peter out in terms of their genetic contribution to this population. And then if we add in the other translocated birds that weren't among those highly successful 16, you can see the same thing. You know, there's they all start kind of contributing genetic material to this population, but quickly also peter out as these highly successful 16 individuals really start to dominate the ancestry of this population. And you can see especially, you know, this one breeding pair here. So I think, you know, the translocations certainly led to growth, which is fantastic because that demographic aspect is critical. That demographic buffer is absolutely essential to the population viability. However, from the genetic perspective, this population is really, the ancestry is really only reflective of a small subset of the founders. And one question I've kind of been asked is, well, you know, is this skew unusual? Let's say if we were to do this kind of translocation again, would this happen just because of chance? Does it boil down to just a flip of the coin? Or is there some aspects of scrub jays that might make this outcome of high skew more likely? And so compared to a very simple model of panmixia, so we're going to assume random mating, uniformly random mating and reproduction, still considering the fact that there's age structure, so mirroring the same demographic trajectory of this population, modeling the monogamy, the age structure, the distributions of longevity. Is this unusual? And what we see compared to this situation of random mating and reproduction is that, yeah, in the contemporary population, it does seem like there are a bit fewer individuals represented than one would really expect. So kind of 90% of the time, we probably would have expected to see a few more individuals contributing. And that really seems to be driven by the residents, that it's the residents that are on the lower end of what we'd expect in terms of numbers or lineages contributing to this population. And then what about that particular highly successful group of 16? Well, here I'm showing, here's the 95% percentile for the contributions. The top of this shade, the light shaded area is the maximum contribution I ever saw for this particular group of 16. And then the observed is that black line. And so we could, according to these simulations, we expect this particular group of 16, given their particular suite of longevities and times of introduction, that they would account for about 52% of the founder ancestry on average from 2015 on, compared to this at least 75% that we saw. And so it's pretty clear that what we observed was definitely higher than I could even ever observe in these simulations. Likewise, for the particular pair WSAK and RLSK, it is possible that you could get that they could have contributed more, but it's very, very unlikely. And they were contributing more than what would be expected 95% of the time. And then you can also think, okay, if you take them, our highest contributors relative to the maximum contribution that any individual could make, how do they compare? And both WSAK and RLSK were making contributions that were higher than what we would really expect, both for a given year and over the course of their average contribution over their time in the mosaic. So, and one thing I do want to point out that I think is interesting for translocations in general, for these small populations that rapidly expand, is that even if the mating and reproduction is random, you can get, as you see here, large skew just by chance. So that is something that can happen and to be mindful of. You know, for example, it is conceivable that just by chance, a single individual could comprise 25% of the population's ancestry. It's just that that happens very rarely. And so why might the reproductive skew that we observe be higher than what we expect under panmixia? There could be a lot of reasons that now it's the area that we want to figure out. You know, there could be spatial aspects, right? And certainly differential fitness. I mean, by definition, the skew is differences in fitness. And I think certainly part of it could be owed, you know, that's generating these fitness landscapes is perhaps the complex social structure of jays. So there's a lot to look into. But what then are the genetic consequences of this? And Raoul has totally spoiled it. But still, to get at it, we sequenced genomes from 87 of the M4 Jays, so 28 of the 51 translocated Jays, residents from all the 4 family groups that were there, and also 1 nestling from each nest in the 2021 cohort. And then we also sequenced a handful of other individuals from other subpopulations for comparative purposes. And you can really see the genomic impact of the high contributors to the population, whereas all of the contemporary core region individuals in this pink, they gravitate, right, genomically towards their ancestors, essentially, unsurprisingly, right? And one consequence of this high reproductive skew or this high variance is that now inbreeding is significantly higher in the contemporary population than it was in the small resident population prior to the translocations or amongst the translocated birds. And they had kind of similar levels of inbreeding. So it's actually exacerbated the inbreeding, these translocations and the subsequent reproductive skew. And then just to give based on a different estimator that I think probably does a better job of relaying what the absolute value, the trends are the same, but what the absolute value of inbreeding is, just because that's valuable information. Average inbreeding in the contemporary population, I think, is around 10%, which is low. You see some high, more inbred individuals. It is not alarmingly high, but it's something to keep in the back of our mind because, for example, work that Nancy has done on the Archbold jays has shown that even low levels of inbreeding, below 5%, can perhaps be associated with inbreeding depression. So it is something to be mindful of. And then lastly, because of this high reproductive variance, it's suppressed the effective size, which has led to this erosion of genetic diversity, such that heterozygosity or genetic diversity is significantly lower in this contemporary population than it was in the population prior to the translocations and also among the translocated birds, which again, between them, their levels of genetic diversity are the same. And so why is all this important? I think it's really because it highlights these mixed conservation outcomes that we have to be mindful of. And that, you know, if you perform these translocations, the demographic growth, the expansion was fantastic. Like I said, that is a necessary aspect, but the genetic and demographic recovery do not necessarily go hand in hand. I think the important takeaway is that even though you see growth, it does not mean that the population, you're overcoming the other small population problems, and you actually have to investigate that. You know, and in the most extreme case, of course, you know, the most dramatic case is, you know, in Isle Royale, where you had a genomic sweep and that led to population collapse. We're nowhere near anything that, you know, dire, where the cumulative contribution of RLS, K, and WSAK is only about the sweep attributable to them is only about 40% as strong as it was in Isle Royale. But it's something to keep in mind. And for translocations in general, thinking that, you know, the simulations have revealed that, you know, even in this fairly optimistic scenario of random reproduction and mating, you can get skew. And it does seem like there is something going on with scrub jays to exacerbate that, perhaps. So keeping that in mind for these types of translocations. And so given that it might be important, how do we keep a pulse on it, on skew? And so just real quickly, everybody here knows how time intensive the population monitoring is to, let's say, construct these types of pedigrees to characterize genetic skew. And so one thing that we want to do is develop a quite simple heuristic, a statistic that can be calculated solely from genetic data that does an accurate job of characterizing, so detecting and characterizing genetic skew. And so we have done that. And I won't go much into detail other than the fact that, you know, if we use this, like I said, quite simple heuristic on, we only sequenced around half of the translocated jays compared to the inference that we can make on the full pedigree with all of them, it aligns quite well. And so the variation in the statistic that I've been calling K does explain a significant amount of the variation, the pedigree-based expected genetic contribution. So it's a quite lightweight, efficient solution in lieu of more intensive demographic monitoring if we're taking genetic snapshots to determine this. And so knowing that in sum, we can use these kind of approaches, so these kind of simple heuristic genetic snapshots to detect and characterize if skew is occurring in populations and monitor it. And so again, the take home is that demographic recovery does not necessarily go hand in hand with a more optimistic genetic trajectory. And so detecting this early, keeping an eye on it will allow for more adaptive management, which meaning that maybe follow-up translocations for the purpose of genetic rescue now are necessary. Like you've established a large population, maybe now it's time to address the genetic aspect of it. And that's it. So thank you.
Are there any questions for either? Yes, Dave. Yeah.
Yeah,
Probably just repeat.
you know, the lineage it seems like they depend a lot possibly on not a lot of habitat turned over in dynamics as opposed to systems that have a lot of variation on families and start hitting birds that are a lot alike. Also that whole
Like more habitat comes online.
yeah, so the dynamics of the demography. Index for those of us who have
Yeah.
almost no money to go on fees.
Yeah, the question is if basically for an index for that, yeah, statistic for characterizing skew, could spatial dynamics and demography be incorporated more into it? Into that simple statistic, actually, perhaps yes. Yeah, the short answer is yes, by putting different, would be a different weighting. It's a weighted statistic anyways. So yeah.
Other Rob said.
Maybe I have two questions. The first one, if I can remove the first one is that it seems like Reed was working on stuff with reproductive skew and RCWs and translocations that would kind of parallel the stuff you're doing with Florida scrub days. And so I guess my first question is are you guys thinking about both of these species in the same vein, or how is that going?
We are working on that as well. Yeah. Reed had approached me to kind of work on that, and I was pretty busy at the time. Now we have a grad student, Alex, in the group, because we thought it was great that both of these, there were parallels, and we could, you know, learn more by analyzing them jointly. So we are there is a study on that. We're analyzing that, has just recently been where it's in revisions now.
Yeah. Are you guys using the same approach? Like how is that?
There are similar, so kind of looking at the expected genetic contributions from the pedigree over time. There was no genetic data for that. So in terms of the pedigree based approaches, yeah, we're taking some analogous approaches to characterizing skew, and it actually doesn't seem to be. I remember that was a big initial concern of Reed's, and it doesn't seem to be having the same effect as it does in the mosaic. Actually, the lineages appear to be a lot more admixed, and there is a more even distribution of ancestries. Though, I mean, of course, it's never perfectly even, but it doesn't seem to be taking over the population in analogous to the way it does here.
I guess my second question is this is not my field,
Yeah.
right? So my question is totally stupid. You've got these two birds that seem to be super breeders, right?
Yeah.
And recall, Reed putting up a figure showing most studies are 5 years and this is the trajectory you get. But if you look over 50 years, you see all this other stuff. Could they be viewed as important super breeders with high reproductive skew that could have impacts on populations because the study hasn't, you could have subsequent super breeders that would kind of break apart some of this inbreeding depression over time.
Yeah, that's a bit of a similar question to something that Fitz and I were talking about this. I mean, the askew isn't bad, right? That is the product of being highly fit. And we can actually tell it's not just that particular breeding pair that is driving the sweep of their lineages. It is also the success of their offspring, because we can know that because their peak ancestry is occurring after they have died. It's being propagated through the population through the successful reproduction of their offspring. And so I think there is inherent good in that, and now it's just monitoring it, because I was saying you can almost, there's maybe a point where you get too much of a good thing, like they are highly fit, their ancestries are propagating well throughout the population like wildfire, but at a point, that will lead to the increased inbreeding, the decrease of genetic diversity. And that's actually kind of, and then at that point, the fitness benefits might be a little bit mooted, which is the good time for genetic rescue, because you still have probably beneficial alleles there, possibly. And so getting those on some different genomic backgrounds could have certainly a benefit for the population.
And you'd use translocations as genetic rescue if you did that, because you could have an immigrant become a super breeder and do the same thing as translocation.
I mean, ideally the type of genetic rescue translocations, they would, the amount of gene flow that would be sought to establish there would be that such that it mimics more natural levels of gene flow. Of course, not dumping in a bunch of birds at once, but that something that would have naturally worked for scrub jays over their evolutionary histories.
All right. Thank you so much, Tyler.